Okay, so thanks, Songtao, for the detailed introduction about feature engineering and feature integration. As you can see, to prepare a good quality of data is not a trivial task. It requires a lot of effort. So do spend enough time on it. So now we are ready to build the model. The very first step is to partition the data into 3 sets, which is training set, validation set, and testing set. We would use training sets to build the model and use the validation set to validate different model configurations, which I will cover in the next slide. And finally, we will pick the best model from model validation and run a final evaluation on the testing set. Okay, so one common pitfall we found is people often only divide the whole data set into 2 parts, which is training set and testing set. And they use testing sets for both model selection and model evaluation. So there's a potential risk of information leakage from the testing set back to the model. So actually the evaluation metrics you've got will be overestimated. So we should avoid this. And as for the solvers, actually there are so many different choices. And back in 2014, there is an interesting paper with title, do we really need hundreds of classifiers to solve the real world classification problem? So in that paper, the authors evaluated more than 200 classifiers or more than 100 data sets. And their conclusion is random forest usually works best. And we also find a similar situation in our real business case. Of course, if you want to really scale up your solution or you want to improve the model running time or scoring time, then you can use modeling techniques such as logistic regression. Given that said, can anyone tell me, is any place that you can further improve about this modeling, model training and validation process? Any place to improve? So here we split to 1 set, training, validation, and testing. Yes, good point. So actually, here is because of the random split, so it's just a random pair of training and validation sets, and we don't fully utilize the whole data set. So usually we can leverage cross-validation to fully utilize the data sets and reduce some randomness in pick a particular pair of training and validation sets. Okay. So next we are going to talk about hyperparameter search. So a lot of machine learning models actually have a lot of parameters to be tuned to achieve the best performance. For example, for regression models, we first need to choose regularization methods, and followed, we also, for each of the methods, we need to set their corresponding weights to set the regularization strengths. And for some of the models, there are even more parameters to be tuned. Take gradient boosted trees, for example. We need to choose number of trees, depth of trees, learning rates, and sampling parameters. For example, how many samples and how many features you want to select to build each of the small tree. And it will be convenient to build some wrapper functions to ease this hyperparameter search in the early problem exploration. And actually, a lot of machine learning packages already provide such utility functions for us. Grid search would be one of the mostly widely used methods to do the parameter search. But for some of the algorithms, actually, there are too many parameters to be tuned. So do a brute force grid search will be very costly. So in such cases, we can choose randomized search or Bayesian optimization, which it always searches for a particular parameter combination which optimizes for the improvement. Okay. So another tip we give is typically we don't want to rerun the parameter search for each retrain. We will only need to do it if there's a huge change in the either data volume or feature distribution. Okay, so next we are going to talk about model measurements. So here I'll list some commonly used metrics to measure the performance of classifiers. I think a lot of you must be familiar with precision and recall. Precision measures the prediction accuracy for all the positively predictions, and the recall measures the percentage or ratio of how many positive labels we have captured by the classifiers. But we need to be very careful about using some of these metrics. Take accuracy as an example, because accuracy only considers the ratio of correct predictions. So there are a lot of data sets, actually, they are very imbalanced. For example, it's often to see more than 99% of the label actually are negative labels. So even a dummy classifier which predicts every sample as negative will achieve a perfect accuracy results close to 100%. So be careful to use of those metrics. Okay, so ROC curve is another chart to describe or illustrate the performance of the classifier. A good ROC curve would have a very high true positive rate while still maintain a low false positive rate. So here you can see the green curve would perform better than the red curve. And we can also use area under the curve as a metric to measure the performance. However, in the real business use case, we found for our business partners which doesn't always have those machine learning or data mining backgrounds, they feel very difficult to understand those metrics. And here I will give you one example showing how we can design particular charts or metrics to deliver those performance lift charts. Okay, so remember Songtao gave you guys an example about how to build a model to identify top users to promote LinkedIn's job seeker subscription accounts. So here the plot, the x-axis actually shows the top members captured by different algorithms, and the y-axis shows the number of conversions by sending out those emails. So a campaign manager will be very clear to see by using these two different algorithms how many emails they need to send out to achieve a particular number of conversions. So for example here, if we want to capture 600 conversions, for the algorithm represented by the green curve, we only need to send out about 200,000 emails, while for the red curve, to achieve the same number of conversions, we need to send out almost 600 emails. So by selecting the green curve, this algorithm can reduce the email volume a lot while still maintain the same number of conversions. And here is a similar curve while we change the y-axis from the number of conversions to the number of conversion rate. Okay, so once we got a good model, the next step is to test the best model on a holdout testing set, which we call the model testing. So the whole process will be very similar to the model validation. But again, I want to emphasize that we need to have a testing data set that is not used in either model selection or model building process. Otherwise, there's data leakage would happen. And so far, we only talk about all the offline validation. There might be some bias or it's not sufficient to prove that the new method works better. So in such cases, we would need the help of online A/B testing. So to conduct A/B testing, we need to first assign or design a testing group and a control group. And we also need to design a bunch of business metrics to measure the performance. Finally, we will run some statistic tests to see either one of the group outperforms one another. And in this talk, I'm not going to tell you guys details about how to set up an A/B test. Instead, I will share some best practice for how to run in an A/B test. Okay, so first of all, always start testing the new exam on a small portion of the users because we want to reduce the potential risk of running a new exam. And second is always measure one change at a time. So that doesn't mean that you can only run one online test on the whole website. It only means that you need to design your experiment carefully so you will be clear about which change caused which change on the metrics. And third one is be aware of the potential bias, either for the time or targeting the population. So take the email marketing model as an example again. So for example, the old exam always sending out emails on Wednesday. So typically, when running an A/B test, you also want to send the emails from the new exam at the same time. Otherwise, there will be some hidden factors that not captured by the model will also affect the final conversion rate. The first one is avoid coupling a marketing campaign with the A/B test. So it's clear that if you're running a marketing campaign, it will affect either the testing group or the control group. So our advice is to first run your A/B test. Once you got good results, then followed by running a marketing campaign. Last one is about multiple testing problems. So remember that we usually will monitor multiple business metrics, and it's common to see that in some of the A/B testing, you will find for some irrelevant metrics, they also pop out as significant changes. In such cases, our suggestion is to use a simple sum of rule to address these problems. So we can use a standard 0.05 p-value for those metrics that are expected to be impacted by the A/B testing. And for all the remaining features, based on our business knowledge, they are not going to impact by the model or the new exam. Then you can use a smaller cutoff, say 0.001 as a cutoff for those metrics. Okay, so once the new exam passed the A/B test, the next step is to deploy the exam to the targeting audience. Again, we will still run or build the very similar feature integration and transformation pipeline. And the only thing we need to do is we need to first define the audience. For example, for a lot of campaigns, we only want to targeting people who are active in the past 4 weeks or past 1 month. So you need to first define your targeting audience, then run your exam on this audience. However, the model deployment is not the end of story. As you can see from this illustration, there might be some user pattern change, or sometimes the feature the distribution will also change, or in some cases, the feature stop generation from the source. So the model performance will drop a lot over the time. That's why we also need a model refreshment or model management. Okay, so in this chart, we show how we do model management in LinkedIn. First of all, we always have a current best so far model, and we monitor its performance change over the time. And we also feed in new training data to generate new model periodically. So how often to refresh model depends on how often the user pattern changes or how many new training data can be generated daily. So for example, if we can generate enough data in 1 week, so we may possibly to build a new model with the difference of the current model. So once we got a new model and a current model, we can always run in another A/B testing to compare their performance. And we can keep the model always up to date. Another point is we can ensemble all the historical models as one of the baseline model. So in this case, all the process actually is running in the back end, and it will keep the model healthy and up to date. Okay, so next, Song-Tao will show some common pitfalls. I mentioned a little bit, but Song-Tao will show you more examples about how to avoid those common pitfalls.
Thanks, Chen. Let's go to this slide. Okay. Can everybody hear me well? Good. So in the last session, we reviewed the common model building process. It's quite easy to follow that process, right? But in reality, many people still complain and struggle about why their model didn't actually achieve the desired performance, or fail to address many of the critical issues. In this session, Chang and I will talk about some common pitfalls and challenges over here. The first common pitfall I'm going to discuss over here is called data leakage. So in 2011, and KDD, there's a paper published that's called Leakage in Data Mining, Formulation, Detection, and Avoidance. They defined data leakage as an introduction of the information about a data mining target which should not be legitimately available to mine from. And here I'm highlighting three common data leakage scenarios. As I mentioned earlier, like there's a common leakage pitfalls we usually have. Like so, for example, in the churn prediction model, as you may already introduced a lot about the context of this model, but from the historical data, you clearly understand that the status of this churn. In this case, the company is our client, and we know like company 1 churned after the end of this contract, and company 2 choose to renew our product. So there always the positive label associated with the company 1 and negative label associated with the company 2, right? So that's the observation. But in reality, like we're talking about a 3-month contract. So you actually can observe this account at different time framework, time windows. So if you observed the company 1 from January, from February, from March, you actually can get more data points and understand the surrounding context related to that data points. So in this way, you actually can introduce more data points in your labeled data to train and testing your model. But with a careless splitting, if you simply do the random splitting on this data set, it's highly likely the entity we're talking about here can appear in both data sets, training and testing. So you end up like leak the information from the training to the testing data. The consequence of this leakage is like it is possible like you overfeed your model to the training data, right? And when you do the testing, so the model already memorized, like as long as I identify the company 1, I can safely predict, okay, I can tell like this count already churned. So in this example, like maybe it's not quite obvious, like, but with a combination of the 3 variables, like the size, the region, and the spending, you can pretty much identify what is the company 1 or company 2, right? And even worse, like after you do the testing, so on the testing data, you actually feel very good. Like you don't actually really realize your model is overfitted into your training. So that's the dangers of this information leakage. If you deploy this solution into production, you will pay the big price of that. The second scenario is leak the future to the past. I mentioned slightly about this kind of leakage earlier. And in this case, like I show you some very simple example. If you do the aggregation, simple aggregation, like using the 3-day price to just to take an average. And in this case, it's very obvious, like you're considering a future price or tomorrow's price into the consideration and actually leak that information into your future. This seems very obvious and straightforward, but in reality, lots of people make such mistake, especially when you're dealing with the aggregated features. For example, taking the monthly aggregation and understand the account assignment or their monthly activities. So you need to be very careful and be clear about what type of. So when your aggregation function is applied, it's applied in the very beginning of the month or at the end of the month. So that will help you to justify whether you really leak the future information into your model. In that paper, they also actually mentioned about a third scenario, is the leak the information from the data samples outside the scope of the algorithm intended use. So it's more often happened in the open data mining machine learning competition, for example, KDD Cup or Kaggle competition. So in 2011, IGCNN competition. So this is the competition you're given 7 million edges derived from the social network and anonymize all the entities. The task is to do the edge prediction. So you're given extra another 9,000 edges and determine whether this edges actually represent the real connection or not, right? The winner team did a very good job, actually. They quickly, through some deep analysis, they quickly figure out this anonymized network actually is Flickr. And then they crawled the website and successfully or creatively denominalized most of the network and edges and entity, and naturally they can decode the validation set as well and predict whether this is the real entity or real connection or not. So they did a very good job to hack the problem, but definitely leveraged some additional information that organizers may not expect them to use. So a little bit of story about this. So the paper also mentioned about some strategy to identify this feature information leakage. One way is the EDA. It's called exploratory data analysis. It's pretty much the idea like you using the analytics software or a visualization tool to help you to understand the distribution or correlation about the data. And if you found a very strong correlation between the feature and your target, you need to think about like whether this is potential feature leakage. It is likely like such correlation might not be available in your validation sets. So another way to address or identify this is to really understand the performance of your model. For example, like you build a stock price prediction model, right? And your model is like the performance looks like that. It's too good to be true. And my advice is that don't tell anybody like your model is like that. So because one possibility is like you really did a good, awesome job, and you're gonna make like tons of money by this model, or you made a very stupid mistake and leaked the future price information into your model, and you don't want to tell anybody you made such mistake. And sometimes the leakage is very hard to detect. So you need to test your model as early as possible in the real world environment before you massively deploy your model. So this gives you some pretty much control of your consequences of the model. The other commonly faced problem or challenge will be that the data is imbalanced. The data set is said to be imbalanced when the binary or multinomial response variables has one or more classes that are underrepresented in the training data. So for example, like your client will come to you like, say, I have a training data like that. So the positive and negative training data, the ratio is 1 to 100 or even 1 to 1,000. It's very big. And so my results are overfitted to majority class. So in this case, like you build a model and the model just, if you just randomly guess and pick the majority class as the prediction result, you still can get a very high accuracy. But accuracy here is a little bit misleading over here. So you need to be careful about your validation method as well. This issue is very, very common. Like, for example, your job recommendation model as prediction model or fraud detection model. So this data, the class imbalance problem is very pervasive and ubiquitous. Misclassification the minority class usually with a high cost. So rejecting the valid credit card transaction may affect the user's experience, but there's no major damage over here. However, if you approve a large fraudulent transaction, there will cause a big financial cost. So this is something you need to really concern about. A solution, the first one is pretty straightforward. Like you can collect more data, or you can consider different evaluation metrics to understand the performance from different angle. For example, using ROC, and you can do the resampling, upsampling, downsampling, etc. I'm gonna quickly run through this because maybe we're approaching the break sooner or later. And you can also choose to use a more robust algorithm. For example, decision tree often perform well on imbalanced data set. And cost-sensitive learning is also another choice. It's a type of the learning in data mining that takes the misclassification cost into the consideration. So just as a reference. So categorical data, so I believe everybody understands what it means. So let's relax a little bit and like take a little bit break and so talking about the categorical data over here. So I'm introducing 3 different category data over here, and so let's use them to maybe review the history of a KDD conference. So who can tell me like the cardinality of the first categorical data? So KDD conference, how many KDD conference hosted in the past? Is that obvious to you guys? This is the 22nd KDD conference. So of course the cardinality over here is the 22. But if you know the historical of a KDD conference, this is originated from as a workshop of AAAI conference. So before the first KDD conference, there's another 4 workshops happened in the past. So the cardinality of that category is 4. And in the past, like majority of the KDD conference actually hosted in US. So, and also recently, there's more countries participated and hosted this conference. So the total hosting country in the past, in this case, is 5. But in reality, in the real model building, platform, so we're gonna deal with a lot of categorical values features with a very high cardinality. For example, industry, country, or city. So and not all of the category or level of those categorical values have enough support. Many data mining software might not be able to handle this high level cardinality features very well. So this is not a concern. For example, R cannot handle the categorical value over 12, 20, 32 levels. So common solutions to address this problem is to reduce the cardinality by grouping the categorical value into higher level ones, or transform your categorical values directly into the binary features. It's pretty straightforward. Yeah, missing data is another common challenge we really face. To make this tutorial more complete, I just cite the literature. Like, this is the commonly used how we classify different type of missing values. To address this problem, you can directly remove those observations from your with the missing values from your data. So this is pretty straightforward, and you can also do the imputation, and or even build a sophisticated model to predict the missing values, right? And another common strategies we introduce over here is to introduce the corresponding dummy variables to indicate whether this feature is a noun or not noun. And so the last but not least, you can choose a model that is robust enough to those missing features. For example, tree-based model is a very good choice. The last challenge that I want to cover over here is called outlier. Outlier is there's two types of outlier. One is the benign or normal outlier. So it's a represented real event. For example, the fraud detection problem, like it's obviously fraud is an outlier, but it's a valid outlier. There's many other erroneous metrics introduced into the model that's considered as invalid outliers, and they were, because of the existence of those outliers, so they will affect your model training significantly. So, for example, outlier value will have a disproportionate weight on the model, or boosting will spend considerable modeling effort to fit those outliers or observations. The common solutions for this problem is to, first of all, you need to be clear, like, so the outliers you just observed is a valid or not valid. And then you can choose like different strategies to address this problem. For example, just simply remove this observation from your training data if you already have enough data, or applied some simple transformation function to reduce the impact. We also, introduced some of the technique earlier, right? And again, so you can smartly choose the better model to handle those outliers. For example, choose a tree-based model, and that's the challenges I want to cover over here. There's a couple more I'm going to cover by Chang.
Okay, thank you. So I'm going to share one of the biggest challenge we have in our day-to-day business use cases, which is about model interpretation. So first of all, why we need to interpret the model? First of all, for ourselves who build the model, we need to debug and diagnose the model. Second, our business partners often ask a question why a particular prediction was made. So actually, they not only care about the model performance, they care more about what is a key driver and why a prediction was made. And finally, it will also help us to deliver the personalized message to the end user. So here I will take one example. Sungta mentioned the job seeker subscription model previously in this tutorial. So let's say we have already built such a model, and we can score all the linking member base. And here we find two members with a very high score. Both of them got a score of 0.9. But if we dig it down, we will find the person on the left, she has a higher behavior score of 0.5, while the person on the right has a higher social score about of 0.4. So that actually they got a high score, but their key driver is quite different. So when we deliver the message for the people who have a higher behavior score, we can mention that you can get more search results by buying premium accounts. While on the right, for the people who has a higher social score, we can mention that 5 of your connection already purchased these premium accounts. And we believe such personalized user targeting can further promote the model performance. Okay. So next, let's take a look at 2 approaches for the model interpretation. The first one on the left is commonly used univariate feature interpretation. It's quite straightforward and easily get a sense of importance for each of the features. And there are a lot of algorithms such as random forest and regularized linear regressions to help us to get an idea about the ranking of those features along with other various feature selection algorithms. But there comes a lot of disadvantages by using a univariate feature selection. First of all, there might some biases in the algorithm. For example, in the random forest, it uses impurity evaluation to ranking the feature importance. So it would favor those variables with more categories. And second is it's often difficult to rank those features with highly correlated variables. And third one is a single feature may contain a lot of noise, so it's very sensitive to those noises. On the right side is what we call the group-wise feature interpretation, and we found it's very helpful to communicate with our business partners. So what does group-wise feature interpretation mean? It means we will group all the massive features into a lot of buckets with semantic meanings. In this case, the intergroup correlation will be much less, and it will be less sensitive to those noises. Of course, it requires a lot of domain knowledge, and we need to spend time with business partners. And here is another example. At LinkedIn, we built some B2B targeting models, and this describes that we group all the company level features into 8 buckets. So some represents the company's engagement on LinkedIn, and some represents their spending. So first of all, it provides the high-level overview and insights. So the business partner will be clear about what is key driver for a particular account. And if he's interested that he can further dig down, for example, he can take a look at what is a key driver inside one bucket, which is product usage, to get an idea about final level predictors. Okay, so here comes the end of the first half of our tutorial, and we feel really grateful about your participation in the early Saturday morning. We feel really incredible, and we hope to see you again after the break. And the session in the next half is Paul will give guys a case study. It's about how LinkedIn do the feature feed ranking, and we will also share some practical solutions to build an end-to-end scalable solution. Yeah, so now it's about 10 o'clock. I think we have a break about 30 minutes. Yeah, thank you.